So, thank you. So this idea of gathering chestnuts is to, during this effortless transition between various fields, sometimes they took 10, 12 years of thinking about things, and every now and then you would understand something. That's a chestnut, okay? So I want to modify that impression. So I wanted to start with, I know this is a mixed audience, so in terms of experience, so I think of mathematics as something built from concepts that young children, even toddlers before they can speak, understand: space, and then when they're a little older, 1, 2, 3, right? Number. Everything is built from that. So often these very sophisticated, complicated webs of information really have very simply stated underpinnings, but it's not obvious, and you have to spend a lot of seemingly effortless time trying to understand it. It takes a long time. You know, getting one every 3 years is good, a good rate. Okay, so and topology is a relatively recent branch. It has antecedents earlier than what I'm going to mention, but the main point came around 1900 when Henri Poincaré took space and broke it up into pieces and then studied combinatorially how they fit together, did some algebra, you might say, and then got interesting new invariants. So the cliche, which is correct, that topologists don't know the difference between a donut and a coffee cup, is true. Because, you know, a donut is sort of something that goes around like that. It's sort of solid, but it has this hole in it. You can sort of link something around, you know, you can put your finger around it and hold it, right? And a coffee cup, let me try to draw a coffee cup. It's thick. It's not a surface, right? It has an inside, it's like a mug, right, going around. And then it has this sort of handle on it. And there are different shapes of coffee cups, but they're all roughly the same. You can deform one to the other. And you notice this main part of this cup can just be deformed down to this part of the donut. I mean, think of this handle as being this handle, and then the rest of this just deforms down to this other piece here. So you can deform a coffee cup to a donut. So a topologist doesn't know the difference. Well, that's correct. I mean, this is the original idea of topology. You have shapes. Some can be deformed to another. Now notice a solid object, like this is some kind of solid fruit, cannot be deformed to one of these two objects because it doesn't have a hole in it. You can't you can shrink this down to a little round ball if you want to, but you know, you can't link something. You can't put your finger through it and hold on to it. You know, if it were very slippery, you'd probably drop it. So, and then you can imagine higher sort of, you can imagine more examples of topology, but I could spend the whole time on that. I'm going to go on though. But this is the first idea, that there's some properties of pieces of space that distinguish them from other chunks of space. And Poincaré broke space up into these simple objects and then saw how they fit together combinatorially and then derived his information. This information is now described in terms of homology classes, for example, of closed curves. So you can take a curve in the complement of the coffee cup or the donut, and you can, it actually may go like back through and around like this well, then that curve can be pulled off, so it doesn't really link. But if it actually went through the hole and came back around and closed up, then you couldn't pull it off. Or it could actually go around the hole 2 times, and then you would associate this kind of a linking number, which is 2, and it could go around back and forth and so on, in and out, back and forth, and every curve that in the complement of the donut has a linking number with the donut. So this starts bringing in numbers into the spatial discussion. So the linking number, okay. And this is expressed formally in terms of homology, which I don't define, but it's a kind of method that does this. Okay, so this first kind of simple idea that topologist doesn't know the difference between a coffee cup and a donut is true and correctly describes something, but that doesn't state what it means. It means you can deform the coffee cup to the donut. And the deformation comes next, the next idea. And then the first idea, though, is formalized with the idea of linking numbers and homology ideas. Okay, so now, right. So actually I wanted to mention, since this is Abel week, Abel himself actually had his hands on this in 1826, 75 years before Poincaré made the introduction. In fact, exactly in this case, when you have surfaces with multiple holes and stuff like that, he actually was studying these with which now are called Abelian differentials. Abel becomes an adjective, which in English comes out as Abelian, and it has to do with this homology, this algebraic structure. But this was not formulated abstractly when he was doing it in 1824, 25. But he actually was doing it without having the abstraction about what does it mean. And he had used these things called Abelian differentials. And then Riemann, 30 years later, 20 years later, developed it further. And then eventually it was so ubiquitous that Poincaré had to say what's going on in a general way. So that's a better view of the history. So, now, today, or in the 20th century, and then today is the 21st century, but anyway, during the 20th century, there was some enhancement of this idea. And the enhancement has to do with these deformations that go between the coffee cup and the donut. There's this deformation. And this is a very important idea in modern mathematics. The idea you have objects that are equivalent, but then there are the equivalences between the objects. You have a way of moving from one to the other, and there might be another way of moving from one to the other. And these two ways may be sort of equivalent, or they may be very different. If I want to get to you, I can go that way around the table, or I can go this way around the table. And those, if I have to slide things on the floor, I can't deform one to the other. I have to go over. But if I was forced to stay on the floor, it was very heavy chain or something, that would be an equivalent. So the idea of equivalences between things, like the way you solve a problem, might be inequivalent ways of solving a problem, is important. So that structure of equivalences between equivalent things, in this case the topological notion of a donut or a coffee cup, is important. And it now is beginning to permeate many different fields of mathematics, mostly algebraic, but I'm expecting it to finally get to really hardcore geometric and analytic things like partial differential equations. It hasn't gotten there yet, but I think it will. Where are my glasses? Am I wearing my glasses? No. I've lost my glasses. All right. There's this very cryptic note here. Oh, yeah. Oh, yeah, okay. I said that, okay. So here's another picture. Right, so let's simplify the above discussion. Let's imagine I have two curves in space that are linked. And we're now in space again. So these are two curves in space that are linked. Those two curves have linking number 1. Oh, thank you. That's a cool thing, when you get to be a certain age, you can't read anymore. But everybody your age, or even, that's not my age, but have to be careful. They have these reading glasses, and so you can borrow anybody's glasses. So let's see if I missed anything. And I can't read it, actually. Okay. Okay, but thank you. I can use this, I'm sure. Okay. So now, in mathematics, you can also, kind of change the rules. I can move this bottom curve, I can move it over here, and I can let it pass, through. This curve's imaginary, so I can let it pass through the curve. Change the rules. The linking number is only defined if you don't let it cross. But if you let it cross, then the linking number is not defined. So I could, move this curve over to here. And the motion would be like along a cylinder. So you'd have curves moving along like this, right? And then, the fact that the linking number is well defined means at some point this curve has to actually touch this curve. So there's a moment there where they touch. Okay? I mean, if the linking number is non-zero and you move it over like that, it has to cut through the curve as many times as the linking number says. Okay, so this is a basic idea of topology. And now you can do something interesting. You can, at the moment it crosses, let's suppose the linking number is 1 and it only crosses one time, you can let's imagine these curves have a direction. You can travel around this curve, and then when you get to the point where they intersect, you can travel around this moment. This was like a movie of this curve moving to here. You can go around this point of the movie in the direction of the curve, and then this direction is like this, and then you go turn and you go around like that. So you can make one curve out of this phenomenon of crossing. And this gives you, in this world where we formalize the idea of topology, you get a sort of an operation where you can take this is like a family of closed curves. Everyone has heard the phrase string theory, and of course nobody knows what it is, and I don't really know either. But this is a family of closed curves, or strings, closed strings. And this is let's see, what's the picture? Oh yeah, here. This is the family. Here's time 0 of the family and time 1 of the family. And here's this other curve, which is just a point family. Anyway, then you can intersect a family of curves with another family of curves and get, for each point of intersection, you can get a third curve, which is the combination of the two. So this is a very simple idea, but this was the subject of the lecture that was referred to 20 years ago It's joint work with Moira Trask, who's sitting over there. It was part of my first efforts to interest in me, and now we have a child who's sitting somewhere else, who's 20. Anyway, so we made a little theory here, which has a name called string topology, and it's the idea that families of closed strings interact by this. This is an example where here's a one-dimensional family and a zero-dimensional family interacting because they're forced to interact by topology of the linking. And you could build an algebraic homological structure on the space of all closed curves inside another big space. So this is a topology with the word string in front of it. Okay, so that's an example. And this was actually motivated by, from my point of view, and from Moira's point of view, was because there was a conjecture of Turayev about closed curves on surfaces. And that conjecture literally turned out to be false, but we couldn't prove it one way or the other. Later, Moira found a counterexample using computers. You could program this structure on a computer. She found an example. Now the curves were on a surface. And this string topology generalized a very interesting theory by Goldman from like around 85, and then extended by Vladimir Turayev in the late 80s. And then we did this work like in the late 90s. It extended their work. This was all in 2 dimensions on surfaces, and this extended it to all dimensions by considering families, which is this idea that the fact that there is this extension is because the equivalences, it's not just the equivalence classes or 2 things that are equivalent, but the equivalence between them has part of the structure, has something to say about what's going on. So this is an example of, you might say, a derived theory that looks deeper into the information of topology. Okay. So let's see. And this field of string topology, so this is like from around 98, and then 2002 it was developed further, and that's, I talked about it here. And then, and it became, it was, some other people, quite a few people were writing papers using this basic structure. And because it fit with algebra. It turns out this idea of deforming objects is very important in all parts of mathematics to study how objects can be deformed. And some deformations are trivial. They don't really change things. Sometimes they change some structure. So the idea of families of structures is another important idea. So if you want to scare a mathematician and he doesn't know whether you're a mathematician or not, and you at a cocktail party or something, you say, have you studied the moduli stack of that problem? And that's the secret word that we're all afraid of, because it's very complicated. When you start making equivalence classes, it has so much structure, only the super experts can understand it. But there's this idea of varying structures, varying the information with moduli. So, and that started with Riemann, who followed Abel, and the tools of Abel went into that. Anyway, that has a purely algebraic life, and it turned out that algebraic life fit very well with string topology. So a lot of people were discussing it in terms of that algebraic discussion. And then, but it's that kind of went its course, and it's still That's sort of, I would call, the number aspect, but the geometric aspect has not been fully appreciated and used. Because you really have these pictures, like you have knots in space, and have a paper, and there's some sort of geometric aspect. You know, when this circle crosses through, it's supposed to cross through transversally like that, and so there's a nice clean cut. And when you look at the local structure, it's the obvious thing of a plane intersecting a line and going through. So somehow this is the moment, you might say. This idea of a plane intersecting a line, that's it. You know, everyone thinks, okay, what's the big deal about that? But that's the most important thing. So appreciating that may take a few years, you might say. But it is, you find out this idea of transversality makes everything well-defined and meaningful. Okay. Glasses again, see what's next. Yeah, so in this string topology, I believe the algebraic aspects are very interesting, but they're untold. There's more gold in them there are hills, you might say, from a geometrical point of view. And one indication of this is a paper with Michael Sullivan and two of our students, respectively, two PhD students, where we apply string topology in this transversal sense, where you kind of eliminate bad intersections. You only consider these kind. And then you can get many invariants of knots and links inside space. So that's like an example of how you can do more with this string topology if you remember the geometry. Okay, so that's my first 2 pages. Okay. Now, this string topology, or this picture of that when you pull something through, there has to be a point where they intersect in the motion, was sort of motivated by my interest in fluid dynamics. And I was astonished to find out in the 90s that a certain equation called the Navier-Stokes equation in 3 dimensions for so-called incompressible fluid motion. And air is regarded as incompressible at some scales, so it applies to air motion too. Those equations that described it, and they go back to Euler, 250 years, weren't known to have solutions or what's the nature of the mathematical structure. And that astonished me because these equations were used where I grew up in Texas in oil fields for the secondary recovery program. When the pressure goes down in the field, you pump water in at other points of the field to make the pressure build up. You can pump more out. And, you know, you have to know where to do it, or else it might take 300 years before the pressure builds up enough to do it. So you have to put it in the right place, and you have to compute stuff and understand what's going on. And actually, 30 years later, I was in Saudi Arabia, and they were at the stage of doing secondary recovery on their big field. So they were studying, had the same problem. So I said, how can this not be known mathematically? And so I started, I was going to try to solve it. Does that mean oh no. Okay. Reacting too fast here. Okay. So where was I? Oh yeah. So I was going to try to really solve it because the people that were working on it were much better at analysis than the actual math problem is perfectly precisely stated, and they couldn't do it. I wanted to find out why they couldn't do it, and maybe there was a reformulation that was easier, and you could do it maybe, or maybe there was a reformulation that was both easier and more useful, because their formulation didn't have a practical criterion about, okay, you prove this thing exists, but can you approximate it in the time less than the life of the universe or something like that, or less than realistic time so you can use the information. So could you find a practical version of the problem, since we now have all this computer ability, which is not that great. I mean, it's great, but it's not that great because, physics happens at a scale from 33 zeros up, computers in the linear scale, and computers can go down to 4 or 5 scales down. And then, because if you do that in 3 dimensions, that's 12 or 15 scales, so that's like a trillion, billion, whatever. And that's it for computers. I mean, so we have a definite scale at which we can work. There's a definite scale at which it happens. And then calculus, the mathematician's wonderful creation, goes down to infinitely many scales. F of x plus h minus f of x over h. You let h go to 0. That means you're doing that. And it turns out to have fantastic consequences for all sorts of problems, but it's not realistic for this problem, maybe. Maybe it is. That's the problem. Maybe it is, maybe it isn't. Anyway, we'd like to have a way of attacking this. How much time do I have left?
You should try to finish in 20 minutes.
20
more.
21 minutes?
About 15 and 20 minutes.
Okay. Okay. I can choose? All right. So I started looking at this equation that defines this. And, you quickly find out where the issue is, actually. It took about 6 months, anyway. An effortless 6 months, okay. The problem is that the equation has a nonlinear term. You have to multiply. You have the time derivative. It's an evolution equation. The fluid is there. It's pointing in some direction. And then it starts evolving by a formula. And the formula involves multiplying a derivative of the motion times the motion, the instantaneous motion, and then a little bit more, and so on. And that nonlinear term, that quadratic term, is what makes the problem. If you just, this is completely elementary, but if you just write down the equation, x dot is equal to x times x. X is x of t, just a real number that depends on t. Well, then you can sort of draw a graph of it. You start out at time 0, t equals 0, like it here. You can, for those of you who've done first-year calculus, you can solve this equation. You can find x of t so that the derivative is the square of x of t, okay? It's a fun exercise. And then it turns out you start out at let this be the value. Well, if you start out at 0, 0 times 0 is 0, x dot is 0, here's the solution. It just stays at 0. If you start out at some little point up here, then it turns out it starts increasing, because x times x is positive, so it starts increasing. And then it turns out over here at 1 over x naught, it goes off the page. And then if you started out at a lower point, it would go off the page like that. Now, this Navier-Stokes equation looks just like that. It's sort of, the time derivative is a product of two things. So maybe it does that. But that's no good, because that's not what fluids do. They know what to do. They seem to go on forever. But it's a much more complicated x times x. It's many variables, vectors that you're multiplying. But one day I had the idea, this is algebra. Even though the x here is in infinite dimensions, it really is x times x, sort of. And it's algebra. So did we have that conversation 3 minutes ago? Okay. So that's 16 to 19 minutes. Okay, so let's see. Okay, 28. Okay, oh, I see, okay. All right, so it's like algebra, but it's the X here now has infinitely many components. So, it's like you have to understand functional analysis and so on. And anyway, it turns out that there may be directions where this happens. And it turns out if you write down, this is another negative chestnut, if you write down a general equation like that with, say, 1,000 variables, and these are vectors, and then it turns out generically and typically this happens. There'll be a direction where it looks like exactly like this. You can change coordinates, it looks like this, so it explodes in finite time. So that's a nice exercise at the next level. Once you know it's true, it's not that hard to prove. If you just write down a general, like 10 of these equations where the right-hand side is a sum of quadratic terms, then with arbitrary coefficients, if you just put on a computer a general example, there would be a direction where it looked like this. So, well, that didn't work. But there's something more intricate going on, because when you have vectors like this and you multiply them to get another vector, that has, if your space is 10-dimensional, say you have 10 components, the number of different possibilities here is like 1,000, 10 times 10 times 10. So, because you have to give 10 of these equations, each one has about 100 coefficients and 10 variables. So I'm doing things approximately. So on the other hand, if you might say, well, many of these different equations are equivalent. I can change coordinates by a matrix. And then, but you say, how many matrices are there in 10 variables? Well, it's 10 times 10, so there's 100. So you have 1,000 different equations, and you can group them into groups that involve 100 components, and that still leaves you with 1,000 minus 100, 900 different types of equations. And only one of them is the Navier-Stokes equation. See, so there are many other equations, and it's special. So I just said the typical one has this bad behavior, but it's a special one. I don't know which special one it is. Okay, so that didn't work. But, okay. So then, well, so this lecture will finish in Roslindale tomorrow. There's a conference on computing and mathematics and stuff like that, right? Yeah, okay. So then there's this idea that comes from physics. It's called separation of scales. And to save time, I actually was going to give a precise definition and a conjecture, but I'll just say this, that, see, when you see water, I remember I spent 81 in Berkeley, in Boulder, Colorado, and every day I'd walk past along the Boulder Creek, and I'd look at the water there, and it's, when I was far away, the water's going like this, and then I'd walk over closer, and it's sort of going like this, and then I'd walk over closer, and it's going like this, and in other words, I was amazed. It has a structure. Depending on how far away I am, it has a sort of structure, and when I go closer, that structure is more refined, and I see it has another structure, but that other structure, finer structure, is consistent with the coarser structure that I observed. That's kind of the idea of separation of scales, that there's some evolution at a coarse scale, there's another evolution at a finer scale, and these are somehow consistent. Whereas the Navier-Stokes equation is only describing what's happening at the infinite scale, down, way below physical reality, because below 33 zeros, 1 over 33 zeros times a centimeter, there's no notion of distance according to quantum theory. So the idea of separation of scales is that there are approximating theories that sort of are consistent, and hopefully there are ones that are at our range of computation. So this is an industry. That was one thing I was amazed about when found that these equations were. There's people all around the world are using these equations to compute fluids and specific problems. The way blood flows through arteries in the heart, because they could deal with aneurysms. If a little thing comes out, a doctor can go in and leave that thing there and support this part here with sewing, and then there's some turbulence going around in here, and the blood sort of flows through like that, and the guy's stabilized. They can do 20 a day. I met a guy at a party once who's telling me this. He could do 20 a day. There are these walking dead men, persons. And then you can do that, and they understand how the fluid is turbulent in here, and then it flows by. And I couldn't believe it. I mean, how can they not know this equation has a math solution when it's used, and then they use it in oil well in the fields and everywhere else. Weather prediction. They're not so good at weather prediction. And where hurricanes hit. I was once in Texas anyway, that's another story. Anyway, so we have this notion of separation. There is a notion of separation of scales, which has a math definition. And so I sort of got this dream or conjecture that there is a finite dimensional ODE that will describe at a certain scale what this Boulder Creek was doing. And then there's another one at a finer scale that's still finite dimensional that's describing what's happening. And these are all consistent. And the limit of all this is this continuum famous equation called the Navier-Stokes equation. So, 8 minutes. Is that okay? Not sure. Yeah, okay. All right, so that would be the conjecture. And then you would hope that not only would it converge and you could prove theorems and stuff like that, but you could also put it on a computer and compute what you wanted to know at the scale that you cared about. And at the Simon Center, which was mentioned before, I've talked to Sasha Abanoff and Zohar Komargatsky and got their perspective on this, and they have a very different perspective that's helpful in thinking about things this way because they understand what are the constants and where things are happening, and so optimistic that this is true. So I make that, so the conjecture is separation of scales exists for three-dimensional fluid dynamics. Okay. So, and then sort of a secret part of the conjecture, and the ideas of Poincaré will be the key to finding this. Why is that? Well, I mentioned Poincaré started topology by breaking space up into these pieces. And then he studied combinatorially how they fit together. And now we sort of know there's kind of a trick. You usually think when you break space up into pieces, it's something like this. But now we know kind of a trick. We also have to add pieces like this. this is part of this secret idea. So we're going to actually, it's like we have lots of pieces of space that are overlapping so that the cracks between the one layer of pieces are covered over. You see how this piece here, there are 4 of these. This is if you're doing a surface, but I'm imagining cubes in 3 space. But see, these squares are kind of rigid, but they could go like that, and then these can go like that, and the whole thing kind of crinkly. But then you sort of pretend there's another plaque here, like a roof, when you do it. I mean, this is probably well known in Norway. You have good roofs. And so you have another layer over the cracks of the first layer. And its cracks, the second layer's cracks, are covered by the first layer, stuff like that. This is Poincare duality, actually. It's part of that homology. This is the sort of finer notion of Poincare duality. So the idea is that the ideas of Poincare will be a key to this. So to study very carefully. So this is, you can take a region of space or make it periodic or something and get a finite picture of space and then go back to this algebra and put in products have to do with, I'll go to 3 space now. Products have to do with, like, here's a 2-dimensional element and it can intersect another 2-dimensional element. This is not a good picture. Right. What? Oh, sorry. Thank you. So some people are paying attention. Good. That's good news. Okay. So see how they intersect, like that's nice transversal intersection. And then you sort of notice, hey, look at these 2 boundaries here. They're linked curves. Oh, wait a minute. So this linking is somehow related. Oh, and this, you get 1 here. And it's sort of like the way this 1-dimensional thing intersects this 2-dimensional thing, that's that point. That tells you the 1. And in fact, it's symmetric. You could look at this one and seeing how it intersects this one, the boundary of this one, how it intersects that one. So this is all part of this x times x algebra. Here's an x and here's an x prime, and x times x prime is this thing, this geometric element here. So the idea is to go to finite dimensions, take this algebraic equation, and carefully study how it looks in finite dimensions and try to understand a very good picture and prove things about it, and then go to a finer scale and repeat it again and try to see that they're consistent. So, I'm on the first half of the second page, and there's hardly anything on this, so it's not bad. So I think it gives you a flavor of what I'm trying to do. So the second chestnut is, so to speak, second or third chestnut is you have to think homologically, but not at the level of equivalence classes. You have to think at a level of geometry where the equivalences are part of the structure, and then interpret the algebra geometrically in terms of this Poincare idea of intersection and linking, and try to get an intelligent model at the finite scale such that when you subdivide and go to smaller little cubes overlapping and everything, the picture you get there is consistent with the picture at the finer scale, at the coarser scale. So that's my conjecture, and this is the idea about how to use it, which is these are using, you might say, using topology ideas to study this fluid mechanics problem in PDE. Now, I've been thinking about this for an effortless 30 years. Okay, thank you very much.